Welcome, Data Sir.
Welcome. Okay.
However difficult life may seem, is only something you can do and succeed it, says Stephen Hawking. A very good morning and a warm welcome to the third day of International Physics Colloquia. The faculty, staff, and students of the Department of Physics, Mathematical Tiruvalla, welcome you all to the International Physics Colloquia, which is an interdisciplinary online platform meant for open discussions and interactions with student scholars. Six lectures on different fields of physics are arranged from 7th September to 11th September 2020. Let's have a look at MTC. Founded on 10 July 1952, Martin College is one of the institutions of high learning administered by mathematicians. More than 80,000 students have blossomed out of the world from this institution so far. The college is affiliated to MC University, Kottayam, Kerala. The college was accredited by National Assessment and Accreditation Council (NAAC) in 1998 and was re-accredited with A grade in 2005, 2012 and also in 2019. Now, I request all of you to get seated in a convenient place away from noises and disturbances. Let me invite Devu Shaji for the prayer song.
You are my strength when I am weak. You are the treasure that I seek. You are my all in all. Seeking you as a precious gem, like to give up, I'd be a fool. You are my all in all. Jesus, Lamb of God, worthy is your name. God, worthy is your name. Worthy is your name.
Let me call upon Dr. Noble B. Abraham, Professor, Department of Physics, Mathematical Tiruvalla, to deliver the welcome speech.
A warm good morning to all the participants. I hope I am audible to everyone.
Yes, sir.
The International Colloquia on Physics was inaugurated by the Honorable Vice Chancellor of Mahatma Gandhi University, Professor Sabu Thomas, on Monday. We had two sessions in the last 2 days. Professor Sabu Thomas presented his researches on nanocomposites and its applications. Yesterday, Dr. Nitin Mohan, IIT Kanpur, discussed super resolution microscopy methods to investigate biomolecular interactions. Now we are into the day 3 of the colloquia on interdisciplinary areas of physics. Today we have an invited talk on understanding the unseen dark universe. Chair of the session, Professor Titus K. Matthew, Cochin University of Science and Technology. Resource person of the day, Dr. Reju Sam John, University of Auckland, New Zealand. Dr. Varghese Matthew, Principal of the College. Professor Santosh Jacob, Head, Department of Physics. Coordinator of the colloquia, Dr. Angel Susan Cherian. Members of the faculty from various institutes, research students, and other participants. It's a great honor for me to welcome you all to this session. Dr. Titus K. Matthew, Head of the Department of Physics at the Cochin University of Science and Technology, is chairing this session. Dr. Titus is a well-known theoretician and is actively involved in cosmology research, especially the recent acceleration of the universe and dark energy. He is currently the president of the Academy of Physics Teachers, Kerala, a forum of all physics teachers in the university and colleges in the state of Kerala. Sir, it's a great honor as the chair of this session. On behalf of the organizers and all the participants, I am privileged to welcome you to this session. The resource person of the day, Dr. Reju Sam John, is a visiting academic in the Department of Physics, the University of Auckland, New Zealand. He is a postdoctoral fellow at the Inter-University Centre for Astronomy and Astrophysics, Pune, popularly known as IUCA. And he is an alumnus of the Department of Physics, Marthama College, Tiruvalla too. His research interests include cosmological simulations of galaxy clusters and group formation. His findings on cosmic rays from galaxy clusters, solving the long-standing puzzle of such emissions, has attracted huge media attention. I am really happy to say that Dr. Reju was one of my early students. Welcome, Reju, to this session.
Thank you.
Dr. Varghese Matthew, Principal of the College, has always been a great support and motivator for the Department of Physics and its activities, in particular this colloquia. I welcome you, sir, to this session. I also welcome the members of the advisory committee, organizing committee, former members of the faculty of the department, students of the department to this session. I extend a wholehearted welcome to all the participants, including a good number of teachers, research scholars, and students from all over the world. We take this opportunity to thank you for your enthusiasm to join this session. Welcome all.
Thank you, sir. Now, the cordially invite Dr. Titus Matthew, Head of the Department of Physics, CUSAP, who is also a member of our advisory committee, to chair this session. His areas of interest are gravity and cosmology. Welcome, sir.
Yeah, thank you, thank you. Audible alle, kelkamalo. Can you hear me?
Yes, sir.
Oh, yeah. Yeah, good morning, Raju.
Good morning, sir.
Happy to see you.
Hi, thank you.
Let me thank the organizers, extremely Dr. Nobel P. Abraham and Angel Susan and other dignitaries in the college for giving me a chance to share this session. In fact, I know Raju for a sizably longer time when he was a research associate, associating for his PhD research with IUCA. And I must say that he is a fresh and a promising candidate in the field of astronomy and astrophysics and also cosmology. And I think after PhD, he took postdoc position at IUCA and also at other in some foreign countries. As it is seen in his biodata, he was presently working in Australia. Am I right, Reju?
New Zealand.
New Zealand, in Auckland.
Yeah.
Yeah. He's also working in USA, Relativistic Astrophysics Group, Georgia. I hope I am right.
Yes, Georgia Tech.
Yeah. So he has got various experience in the field. So I think he is the right person to speak on this topic. And especially he is an alumni of Marthoma College. In that sense also, it is very nice to have him for this colloquium. So with this, let me invite Dr. Reju for this nice presentations. Over to Reju.
Thank you, Titan sir. Am I audible now, right now?
Yeah, yes.
Thank you. I think you can see my screen right now.
Yeah. I think there is a slight problem. Yes, the screen is visible. Yeah. You may put it in presentation.
Yeah.
Yeah, it is seen.
Thank you.
Yes, sir.
Thank you, Titan sir. First of all, I would like to thank all the organizers, especially Dr. Noble and Dr. Angel for arranging this workshop, this seminar, and inviting me to present some of the fundamentals of cosmology and our current understanding of the universe. Just a minute. For the time being, I will switch off my video because that will help in conserving bandwidth. Okay, sorry for the inconvenience.
It's okay.
Okay, once again, thank you very much for inviting. So this is my title. In this talk, I will try to introduce the fundamentals of our current understanding of universe in a very quick manner. So this is my plan of the talk. So what I follow is, I will follow a scientific method. First, I will introduce some of the fundamental observations on which our modern cosmological model built. Then I will explain what is that current standard cosmological model. Then, as we know, any theory should give some predictions that we should verify experimentally or observation. Here also, I will try to give you one of the prediction of our current standard cosmological model and how we observationally verified it. So that will come in the first part of the talk. And the second part is, I modeled it as the dark universe, where I will try to explain some of the observation which changed our entire understanding of the universe. So that will come under the second section. Then there's a third section. In this section, I will try to introduce some of the problems faced by a cosmologist or an astronomer and how we solved it. So this third section is an optional one right now, because if time permits, I will go to this section. Otherwise, I will skip this third section. Okay. So you all know it's not possible to cover the entire evolution of universe. It is about 13.8 billion years of cosmic evolution. One cannot summarize this evolution in a single talk, but still I will try to summarize the important epochs and the important events that happened over the period of last 13.8 billion years in this talk. Human curiosity. So we humans always have this curiosity, and we always think about such questions like, where do we come from, where are we, what are we, where are we going? And these are the fundamental questions always guided humans to the progression. So for a cosmologist also, for an astronomer also, these questions were very, very important from the early times. And this curiosity motivates its structure, its origin, its evolution, the density of the universe, the principle that governs the universe, what the universe is likely in the large scale. So these are this curiosity motivated us to ask these questions, and people were trying to answer these questions for over thousands of years. And our cosmology is ultimately based on observations and trying to answer those questions. So if you are listening this talk some 2000 years back, then this should be the picture of cosmology. That's an Egyptian cosmology. They believed that they were living on the surface of a goddess named Geb. And if you are listening this talk some 1000 years back, then this could be your model of cosmology or picture of the cosmology. That was a Greek cosmology where they believed that Earth was the center of the universe and everything else were revolving around the Earth. So this was a cosmological picture some 1000 years back. But this is our current picture of universe, current understanding about the universe. Even this one is very, very different from the past 30 years. So if you are listening this talk some 30 years back, then this curve will not be there. This one. This happened very, very recently. So I will explain. We will come back to this slide later in the talk, and I will explain what are those epochs and what is our current understanding and what this picture meant by. A caution. So we are going out from our Earth. So the time scale and the distance and the mass, everything we have to invent. We have to use some different units for measuring time, distance, and mass. For an astrophysicist or a cosmologist, we always mention time in giga-years. That means 1 giga-year is equal to 10 to the power 9 years, this much second. We will tell that the age of the sun is 4.57 giga-years. What that means, 4.57 into 10 to the power 9 years. Like the distance, we always express distance in megaparsec. 1 megaparsec is equal to 10 to the power 6 parsecs. That one is equal to this much of kilometers. We will tell that distance to our Andromeda galaxy, that's the nearest galaxy, is 0.75 megaparsec. Mass, we always represent mass in solar mass. The solar mass means mass of the sun. 1 solar mass equal to this much of kilogram. Okay, let's come back to a serious business. As I promised you, every science or even cosmology based on some observations. Then we will make some hypothesis. Then we will test that hypothesis. Then we will make some theory. That theory will give some prediction. That prediction we should again observe it, then verify it. If needed, we will modify it. the current understanding of cosmology or the current cosmological model is called Big Bang theory in a popular language. In a technical language, it's called lambda CDM. I think tomorrow Dr. Srinath will introduce the general relativity and what lambda CDM model meant by. So in this talk, I will prefer to use the term Big Bang theory. So our current Big Bang theory is based on these two fundamental observations, or three observations. First one is Olbert's paradox. Second one, Hubble's law. And third one, cosmic microwave background radiation. So some of the observations on which the modern cosmology based are highly complex, like this. The CMB observation, we need a very highly complex equipments and data analysis and sophisticated many things. But the first two things, the Hubble's law and Olbert's paradox, doesn't require any sophisticated items. So let's see what are these observations. So what strikes you of the night sky? Yeah, since it is a virtual meeting, I will not get any answer. What is it? It is dark. Then let me make this point clear. If you look our sun, we will get a flux density of 5 into 10 to the power minus 3 watts per unit area from a unit angular area. Let me explain one more thing. During the daytime, if you look at sun, you will get a flux density of 5 into 10 to the power minus 30. You will get 5 into 10 to the power minus 30 watts of energy or flux per unit area in the earth from a unit angular area from the sky. But during night, you will get only this much of flux density, light flux density. So night is dark, but day is very bright. The fact that night sky is dark at visible wavelengths instead of being uniformly bright with starlight is known as Olbert's paradox. So you may think that, okay, what is this? Let me explain it a little more detail. Okay, imagine you are in a big forest, a large enough forest like this. Okay, then your every line of sight ends at a tree. Let me tell one more time. You are in a very big forest like this, and your every line of sight ends at a tree. Okay, imagine the same thing. If you are in a large enough universe, suppose you are standing here, okay, then the every line of sight ends in a star, and the sun's flux density is this much. You may have infinite number of stars like sun in the night sky. So your every line of sight should enter in a star, and your night sky should be bright as this much there. But this is not happening. So that is the paradox. Why this is happening? What are the possible resolution of Olbert's paradox? Yeah, we made two assumptions while making this paradox or while making this argument. Our first assumption was the universe is infinitely large. If our universe is not infinitely large, our every line of sight will not end in a star. That was our first assumption. The universe is infinitely large. How we can resolve? But our night sky is not bright. How we will solve? If the universe only extends to a maximum distance, then every sight line will not end in a star. And second assumption, the universe is infinitely old. Okay, what is the solution? If the universe has a finite age, then the distant stars haven't had enough time to send us the light message saying that we are here. So, from the Olbert's paradox, what we understand? We understand that, yeah, the universe is not infinitely large and the universe is not infinitely old. If the universe is infinitely old and the universe is infinitely large, then our night sky should be bright as our day sky. So this is a very, very, very basic observation. We don't need any sophisticated equipment to understand or to make this observation and conclusion. So this is the very first fundamental observation on which the modern cosmological model built. Let me specify one more time. With this paradox, we should understand that our universe is not infinitely big and not infinitely old. That means it has a beginning and it has a physical boundary. So let me go to the another observation. So this happens in early 1920s. Exact date may be 1928 or 29. There was a astrophysicist called Hubble. So what he was doing, he was taking the photograph, not photograph, he was marking the spectrum or taking the spectrum of nearby galaxies and distant galaxies. Then, for his surprise, what he observed is like this. For example, if you observe in your laboratory frame, if this is the spectrum of a light, what he observed is that the spectrum of galaxies, all the spectra shows a redshift. That means all the spectral features shifted towards the longer wavelength. Look, red is the longer wavelength and blue is the shortest wavelength. All the spectral features is shifting towards the longer wavelength, and also he observed that the amount of shift, look, the amount of shift increases with the distance. That means, what do you mean by that? The more distant galaxies are moving away faster. Let me explain this in a different way. Let us assume this is your toy model of universe. Here we have few galaxies, okay, embedded on a fabric of one-dimensional space. Look, here we have 1, 2, 3, 4, 5, 6, 7, 8 galaxies, and this can be extended also. It can be 10, 100, or how many number you want, you can add. We have some 8 galaxies embedded on a one-dimensional fabric of space. Then, after some time, delta t, what happened? Somebody stretched that fabric of space. Our space got extended, expanded. Our space got expanded. That's what happened after a time, delta t. I'm showing you the same in this picture. At time t, this was the fabric of our one-dimensional universe. Then after a time, delta t, what happened? Somebody stretched, or not somebody, I've just taken that word, our fabric of the space got stretched, got expanded, and we are sitting here in our Milky Way galaxy and looking these events. What happened with the delta t time difference? Our galaxy is here, it's here, and this galaxy should have been here if the space is not expanded or stretched. But since the space which our galaxies are embedded, galaxy went here. The same happened with this one. It should have been here if the space is not stretched or expanded, but it went here. It has our universe went through a uniform stretching, uniform expansion. Same with here. And let me say, this movement, this displacement is delta x1. And this displacement is delta x2. Okay. Then what is the definition of velocity? Velocity is equal to delta x by delta t. So we will see that delta x2 equal to, so delta v2 equal to delta x2 divided by delta t, and delta v1 is equal to, velocity v1 is equal to delta x1 divided by delta t. But what we infer from this, due to the uniform stretching expansion of the universe, this galaxy, the farther galaxy, appear to move faster than the nearby galaxy. This one. Why? Because delta x2 is more than delta x1, so delta v2 will be more. What was the Hubble's observation means? It means our universe, or the space of our universe is stretching, is expanding. That's why faraway galaxies are expanding, are moving faster than the nearby galaxy. That's what we should understand from Hubble's law, or that's what actually happening behind the Hubble's law. And this was the original diagram made by Hubble. In this axis is the distance, and this axis is the velocity of the galaxies going away from us. And this relationship is known as Hubble's law. And in every direction we look, the faraway galaxies are moving away from us, except some few of the nearby galaxies, like our nearby galaxy, Andromeda galaxy. Actually, that galaxy is coming towards us in, I think, in few billions of years. Andromeda galaxy will collide, since these two galaxies are coming closer day by day. But all the faraway galaxies are moving away from, in all direction which we look. Then people can ask one question: does this mean we are right in the middle of the universe? And the answer is no. We make the assumption that we are not in a special place, and the universe look approximately same to all observers. And this is called cosmological principle. So let me state what is cosmological principle. Principle states that the large-scale universe is both homogeneous and isotropic. You should keep this word in mind. Only in the large-scale universe, universe is both homogeneous and isotropic. What does this large-scale means? You should think about a universe which is large as 100 megaparsec. I mentioned you earlier what, and 100 megaparsec means something like 3.2 into 10 to the power 8 light years, or it will be like 3 into 10 to the power 21 kilometers, or just write 3 and then 21 put 21 zeros, that much kilometers. If you observe universe above that scale, then the universe will be homogeneous and isotropic. What homogeneous means? Same in all locations. This means that there is no preferred observing position in the universe. And isotropic means universe is same in all directions. This means you may see no different ways as you look in different directions. Is this true or false? Obviously, this is true. We have supporting evidence, like we have some surveys called 2-degree field galaxy redshift survey. This is our Milky Way galaxy, and our sun is situated here, and we have this telescope situated in our Earth and looking to the northern sky and the southern sky with a 2-degree field of observation. And what they get is this amazing map of our universe. In this map, every point is a galaxy. Every point is a galaxy, and you get a nice filamentary structure where you cannot say any preferred direction, or you cannot say any preferred point of observation. If you look from this point, the surrounding will be same. If you look from this point, the surrounding will be same. Everywhere you can find structures like filamentary structure like galaxies, then some voids in between them. So in a large scale, above 100 megaparsec or above 3 into 10 to the power 21 kilometer scale, our universe is homogeneous and isotropic. Let me go to the... So, what could we understand from these two observations? First one is Olbert's paradox. What was it? The night sky is dark. And what was the resolution? The reason for that, the universe is not infinitely old, or universe is not infinitely, and universe is not infinitely big. And Hubble's law tells that, just think about our toy universe model. Why Hubble's law is happening? Because the space of the fabric of the space on which the galaxies or stars, whatever thing embedded, is expanding. So if we think backward, at some point in the past, the universe was a hot, dense singularity. Okay. If we imagine playing the movie of the universe in reverse, the density would increase as we went back in time until we reached the time when the density of the universe was infinite and all of the space was just contained in a single, contracted in a single point. And this instant happened 13.8 billion years ago. It is the Big Bang and represent the limit of what we can extrapolate. You cannot ask me, one cannot ask what happened before Big Bang or what caused the Big Bang. From our current understanding, we are unable to answer such questions. We can discuss what happens after Big Bang, what happens some 13.8 billion years ago. But one cannot ask the questions, what happened Big Bang? So this Big Bang model has essentially nothing to say about the Big Bang itself. It describes what happens after the Big Bang. And the Big Bang was not an explosion in space. This point should be stressed over and over and over, because everybody, I think almost all of the people, think that the Big Bang, you think Big Bang as an explosion in the space, like the very common understanding or explosions that we know, like a bomb explosion or something else. But Big Bang is not like that. It is an explosion of space. I'm stressing this again and again. Big Bang was not an explosion in the space, but an explosion of the space. That means the space itself created and exploded at that point of time. And we call that point of time, that event, as the Big Bang. Then the space is expanding. As I showed earlier, not the galaxies are moving away from each other. The space on which the galaxies are embedded is getting stretched. It is expanding, and that is what the Big Bang called. It did not happen at any particular location and spread out from there into some pre-existing void. It occurred everywhere at the same time. So you should keep this concept in your mind. I'm going to emphasize one more time. The Big Bang was not an explosion in space, but it is an explosion of the space, and it did not happen at any particular location, but it occurred everywhere at the same time. As I pointed earlier, now we have some observations. Based on our observation, we made some theory called Big Bang model, saying that past something like this much time ago, our space exploded, explosion of space. In a scientific model, this should be falsifiable. That means this should make some predictions that can be observationally verified or examined. Then only we can call it as a successful theory or model. And the prediction of Big Bang is that if the universe was denser and hotter in past, then we should see the evidence of the leftover heat from the earlier universe. And 1948, these people published a very nice paper showing that if Big Bang theory is true, then we should find the evidence, the residue of our early hot dense past. Okay, and they calculated the temperature of that black body also. It was 5 degrees according to their calculation. Let me explain one little more clearly here. So, as I pointed, some 13.8 billion years back, our universe was very hot and dense. Then there will not be any neutral atom because it's very hot and dense. Then what? Then all the atoms should be in an ionized form, like protons, neutrons, and electrons are separate, like here. Okay, and if the universe began to hot and dense, as the Big Bang model claimed, then the radiation, the photons, and the matter should be in a continuous scattering. Let me explain in a different way. Suppose you are standing inside a fog, a thick fog. Can you see anything outside? No. Why? The photons, the light particles, are continuously scattered with that fog particles and cannot escape from the fog. It cannot go outside, or any other photons from the outside can come inside, so you cannot see anything from the outside world. That means inside that fog, the photons and the fog particles are in a thermal equilibrium. Okay, another example I can give. If you are looking at the sky, in a cloudy sky, you cannot look through the cloud. Why? The photons inside, the light inside the cloud is in continuous scattering with the cloud particle. It is unable to escape from the cloud so that it will not reach your eyes. The same situation was there at the beginning when the universe was very dense and hot. So the photons were in thermal equilibrium with the protons and neutrons, photons and electrons. Then what happened? As time progressed, universe expand and cools down, and there happened a time like this, and we call that time as recombination era. And the naming is bit confusing because the people named it recombination, but there was no neutral atom before that, so there is no point of combined form, and the naming recombination is something like illogical. But what to do? We should follow the convention. People named that point of time as recombination era. So what happened this recombination time? Since the universe was expanding, that the density, it became less dense and less temperature. Then what will happen? This electrons, neutrons, protons will combine and form neutral elements like hydrogen and helium. Now, these photons, which were in the thermal equilibrium with the matter, get decoupled and is free to move around. So this was the prediction. Okay, if there was a hot and dense period of time in the past, then we should observe photons which bear the signature of that thermal equilibrium, from everywhere, every direction we look. And that radiation was named as CMBR, Cosmic Microwave. Let me explain each and every term one more time. Cosmic means the origin of that radiation is cosmic in nature. Then background, why? In every direction we look in the sky. So that was a prediction. Then this happened. This process predicted in 1948, and nobody was able to observe these things till 1965. In 1965, two people, this Wilson and Penzias of Bell Telephone Laboratory, they were designing a very sensitive antenna for the telecommunication. For their surprise, this was the cosmic microwave background radiation predicted by the Big Bang. This was the same thing. They were observing the same prediction. The very perfect black body radiation, which bears the signature of recombination era. That was these people observing in early 1965. This is that CMBR radiation, and the most precisely measured black body spectrum in the nature. These error bars here, this point is the data, and the line is the 2.73 Kelvin black body radiation theoretical model, and each point is the data, and the error bar too small to even see in an enlarged image. So what we have plotted here is 400 times the standard mark, not the error bar. Error bar times, or a sigma, the standard deviation times 400 times, in order to see that error bar, in order to magnify that error bar. So this is the most precise measured black body spectrum in the nature. So let me conclude the first section of the talk. So what we have understood here, with the Olbert's paradox and Hubbles law plus CMBR, a universe described by Big Bang model that begin in a hot dense state a finite time ago, and the cosmological principle says that our universe is homogeneous and isotropic over the large scale, and in the past the universe was more nearly homogeneous and isotropic. Let me come to the picture which I shown in my first few slides, this one, and let me explain what this is. As we pointed, our universe begin at a singularity like this. This is called hot Big Bang. Let's not try to answer the question, what caused the Big Bang? Let's take the Big Bang as the starting point of our history like this. Then the first most important epoch is called inflationary epoch, this period. In this inflationary epoch, this was an epoch of heavy expansion of the young universe, in which the volume of the universe is estimated to have increased by a factor of 10 to the power 78, and this happened only for 10 to the power minus 32 seconds after the Big Bang. And after the Big Bang, just after the 10 to the power 32 second, now our universe is about the size of a typical galaxy. Here, this doesn't mean that the inflation of the universe itself stopped, but just the rate of the expansion dramatically have been expanding until today. Or recently the universe is accelerating, the expansion of universe is getting accelerated here at current epoch. Okay, at 10 to the power minus 6 seconds after the Big Bang, the heavy expansion has lowered the temperature sufficiently for the quarks to form and be stable. Until 10 to the power minus 5 seconds, the universe was composed of a quark soup and accumulating of very basic building blocks of matter like quarks, leptons, anti-leptons, gluons, and some extremely high energy radiations. But after 10 to the power minus 5 seconds, the universe had further expanded and cooled down enough to form stable protons and neutrons out of this quark soup. At about 1 second after the Big Bang, the temperature went down to about 1000 times the temperature of Sun's core. You can now expect the proton would fuse to form heavier elements since we have all the ingredients for the nuclear fusion. A few minutes later, after the Big Bang, the temperature and density dropped down enough to pave the way of our era of nucleosynthesis. That means all the other heavy elements, not all heavy elements like hydrogen and helium formed there, and some of the elements up to iron. This is what happened over here after nucleosynthesis. Then comes our era of recombination and the cosmic microwave background radiation. It happened something like 380,000 years after the Big Bang. And then, for a large period of time, our universe was dark. And this age is called Dark Age. Nobody knows how exact was the extent of this Dark Age. Why this happened? The Dark Age are the era when the universe was already transparent to many wavelengths, but there was no stars yet to be formed. There was no stars, so there was no ionization, no emission of light. Until at some point here, when the first stars formed, so till now we are unaware about the exact number or years after Big Bang when this event happened. People are telling us it happened something like 13.3 billion years, like that. But we don't know what is the exact time of formation of first star and the ionization of the medium. And this period is called reionization. There was a period called recombination here, and now this period is called reionization. Why it is called reionization? Because stars form, it starts emitting light, and that radiation again starts ionize the neutral hydrogen and helium, and this epoch is called reionization. And our current epoch is the reionized universe. This is our current understanding of the universe. So here, the first section is ending here, and let me go to the second section of the talk, where I will try to outline some of the observation which changed the current Big Bang model. Okay, in 1933, there was a Swiss-American physicist called Zwick. People call him mad physicist due to his eccentric activities or comments. And he made a very, very significant observation about the coma cluster, or coma cluster's missing mass. Then, for the next 30-40 years, nobody else look into this matter seriously, because people think that this fellow is eccentric and he's telling something blah 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 blah. Galaxy is something like 300 us. Zwick was measuring of individual galaxies. So these are some of the galaxies in the coma cluster, and Zwick was measuring the radial velocity of these galaxies. Okay, and comparison with the sum of the visible mass in this coma cluster, and what he found out is that the mass in the coma cluster is not enough to hold these galaxies. Let me tell one more. Measuring the velocity of individual galaxies in the coma cluster and measuring its distance from the center of the cluster. Okay, it should be 2r here instead of r. Then, yeah, he calculated the mass required to hold the cluster together. It should be m is equal to v square by r. How this equation came? Yeah, I will explain that here. It is just the just equating the centripetal force and the gravitational force. The centripetal force mv square by r should be equal to gm m by r square, where m is the individual galaxy mass and this one is the total mass, visible mass of the galaxy cluster. Then if you rearrange for m, we will get m is equal to v square by r. He measured this v and he measured this r. This is the Newton's gravitational constant, and then calculated the visible mass. He found that he calculated the visible mass. He found that the mass to hold this coma cluster in a gravitationally bound system. He concluded mass or dark matter. He coined the term in early 1933, but nobody took it seriously. Then he pointed out that in order to sustain the coma cluster in its current state, there should be some extra mass, missing mass, that we are unable to visibly coma cluster. So that was the missing mass observation made by Zwick in early 1933. Before going to the next observation, let me give an example of solar system. Okay, this is our solar system, and we all know that the inner planets orbit faster than the outer planets. We all know these things. Okay, then let me theorize the same thing, and the same it is called the plotting the rotation curve of solar system. Okay, since the planets are orbiting since the planet's orbits are nearly circular, the centripetal force experienced on each of the planet should be equal to the gravitational force. Then only the system will go like this or survive like this in a gravitationally bound state. Then we can invent mv square by r is equal to gm by g, where m is the mass of the planet and capital M is the mass of the sun, where all the mass of the solar system exists. If you rearrange for v, the orbital velocity of each planet, you will see that it is independent of the mass of the planet. It is v equal to root of gm by r, or v is proportional to 1 by root r. If you plot the curve of 1 by root r, it will come like this. And each dot are the here each dot is the orbital speed of each planet, and in this axis what we plotted is the mean distance from the sun. Each planet exactly obeying our 1 by root r curve, and this is the rotation curve. So what should be the takeaway point from this slide? If a system is in gravitationally bound state, then the orbital speed of that object should follow the 1 by root r rule, like this. Then later, after this civics observation, some 30-40 years, nobody took it into a serious consideration. In late 1960s or early 1970s, an American astrophysicist called Vera Rubin, she took this seriously, and she made a statement. Okay, let me plot the rotation curves of galaxies in a cluster. How we can do it? For example, this is a typical spiral galaxy. We have 3 points A, B, and C. Okay. Since this is in spiral galaxies, all the objects are revolving around the center point. Since the object at point A is coming towards us, then the light from that object should be blue shifted, and the object at point C are going away from us, then the light should be red shifted. Then we should observe a red shift. From measuring this blue shift and red shift, we can measure the velocity by which, or interaction like gravitational friction, whatever interaction we know, it will happen there. But as I told earlier, if there is a matter which we named dark matter is presented there, what should happen to that matter? It should not interact with our normal matter. It should pass collisionless. Okay, that's the prediction. Or the surprise, or as an obvious thing, later in 2006, these people, Clover et al., made this very important observation. So what is this? In this map, this is the optical image of our coma cluster with overplotted mass contours. So these contours represent the mass in our coma cluster, in our blood cluster, with the optical image. How we take this mass, how we made this mass contours? There was a method called gravitational lensing, and gravitational lensing itself is a very big field, so I am unable to explain what gravitational lensing in this talk, but you just understand that it's a method of measuring mass in some point in the space. We can use gravitation, it's not a method, we can use gravitational lensing to measure the mass in some point in the space. And in this plot, we overplotted this mass contour with the X-ray observation with the help of Chandra telescope. What you can see here is amazing thing, very, very amazing thing. It can be seen that most of the matter resides in a location different from the plasma. You can see X-ray from the space where most of the ionized plasma exists. So all the ionized plasma is located here, and most of the mass is located at here. Why this is happening? Yeah, plasma will undergo a lot of interaction other than gravitation. On the other hand, dark matter will not undergo any interaction other than gravitation. It will pass. So Clover et al. Conclude that the spatial center of dark matter concentration was mostly segregated from the spatial center of baryons observed. Statistically, the study claimed that there was only a 1 in 10 to the power 15 chance that this spatial segregation was a fluke, or in other words, they were damn certain that what we see is dark matter and baryon interact differently during a collision. This was an indirect evidence or proof for the existence of dark matter. I will conclude with this is my last observation, which I intend to discuss here. In 5 minutes, I will conclude. So, in early 90s, we were certain about the expansion of the universe, which we already discussed, and the universe might have enough energy and density to stop its expansion. Because look at here, our universe is full of objects like stars, galaxy clusters, and everything, and our universe is expanding also, that we know. But due to the gravitational pull, this expansion should slow down. Okay, it's a very, very logical argument, isn't it? We have a lot of objects here. It should gravitationally pull everything to the center of gravity. Then the expansion of our galaxy, or the universe, should be slowed down. Theoretically, the universe had to slow. The universe is full of matter, and the attractive force of gravity should pull everything towards its center. So, to verify this statement, or verify this thing, two independent teams led by Sol and Brian, one is in, I think, Penn State, and other one is from, I forgot their institutes. They started observing the most distant supernova. An explosion. Supernova is the explosion of it's an explosion in space and a dying state of a star. And the supernovas, especially the type 1 supernova, are known as standard candles. What that means, wherever this type of supernova occur, its luminosity should be same. That is what meant by a standard candidate. Let me tell one more time. If you can measure a luminosity of a nearby supernova, okay, then the faraway supernova, this supernova also produce same amount of light. It's called a standard candle. But due to the distance, its luminosity will decrease. Okay, so this is called a standard candle. Then these people found some 50 odd distant supernova whose lights seemed weaker than expected. Because it's a standard candle, people know how much light should come from a supernova event. But the distant supernova which they observed, whose light seems to weaker than what expected. This was contrary to what they have envisioned. What they were observing, if universe were universe expansion is slowing down, then this supernova should come near to us, and its brightness should increase. But they found is this. What they found was the light seems to getting weaker and weaker and weaker. If the cosmic expansion has been losing speed, then the supernova should appear brighter, as I pointed. However, the supernovae were fading as they were carried faster. They were carried faster and faster away with their galaxies. To surprise, what they concluded was the expansion of universe is not slowing down. Quite to the contrary, it is accelerating. With this observation was happened in 1998. They concluded that our universe is not only expanding, but the expansion is getting accelerating. Oh, this was a surprise. We all know that our universe consists of only normal matter. Then we now realize there are dark matter instead of that. Then there are some neutrinos, there are radiation. If these are the only things present in our universe, then how can this accelerated expansion occur? The universe can expand just fine with those things, but the distant galaxies should only show a slowdown with only the presence of these things. The observation of acceleration means that there was something else in addition to these things, and that is why something like other than this thing, and that is just present, it was dominant. and we named that thing as the dark energy. It overcomes all the gravitational pulls and making a accelerated expansion of the universe. We don't know what that energy is. We know only there is something existed or dominated in the the universe and accelerating the expansion of our universe. And this is our current understanding of our universe. Our observations with many telescopes in many different wavelengths of many different types of objects have told us that the universe by and large is occupied by the things we don't see. So to be more precise, we now say that 69% of our universe is made up of an energy called dark energy. We don't know what it is. Dark energy. So when we come up with all sorts of matter and energy in the universe, 69% of it turn out to be a form of energy that we don't have any direct understanding of. This is the energy that makes our universe expand faster than it should. And we have many different observations that point it to that way. of the type that is more matter-like, we have found there is a 26% is dark matter. The dark matter is the type of matter that we can feel through its gravitational interaction. It doesn't emit light at all. In fact, it does not have any interactions like magnetic, electric, or any other type of interaction apart from its gravitational interaction that we can directly observe with the telescope. Of everything we look at, only 5% is the things that we have tested. Only 5%. Meaning the stuffs that make up our bodies, our planets, our stars, stuffs between the stars, the gas cloud, and anything else in the universe that shines and whose light reach our telescope is only 5%. It consists of, in that 5%, almost 4% is the hydrogen and helium. Then some 0.5% is our stars. Then from 0.3% is neutrinos, and then some only very, very, very small amount, 0.03% is only the heavy elements. So this is our current picture of universe. So as I pointed earlier, since time is not permitting, I am not going to go through the third section of my talk. I'm just skipping this thing, and yeah, that's all.
Thank you, Reju, for that wonderful session. We have a couple of questions. Irene, can you please unmute yourself?
Yes, sir.
Please ask.
Sir, can you explain the recombination process that you have explained earlier?
Recombination?
Yeah.
Okay, yeah, just a minute. Okay, so this is what you asked.
Yes, sir.
So the Big Bang theory says that at some point in the past, the universe was very hot and dense. In a hot and dense epoch of time, all the matter should be in a ionized soup or plasma form. Okay, there the photons will be in continuous scattering with this matter, just like as we are inside a fog, we are unable to see what happened outside the fog, in a thick fog. Why? The light photons are continuously scattering with the fog particles. It is those particles are unable to escape from the fog. As I told earlier, if you look the sky also, if you look the sun also, you are unable to see inside the sun. Similarly, you are unable to see through the clouds, through a thick cloud. Why? The photons will be continuously scattering with the cloud. So those photons cannot come outside from the cloud. The same thing is happening here. Since it was dense, the photons is continuously scattering with these particles like protons, neutrons, and electrons. Okay, now what is happening? Our universe is expanding at time progress. Okay, at some point of time, what will happen? The temperature will drop down. Since the universe is expanding, the temperature will come down. Okay, and there will be a very good time for the protons and neutrons and electrons to combine and form atoms. Okay, earlier it was very high temperature and very dense, so this combination will not happen. As temperature go down, there will be a suitable, or there will be a amp temperature at which this nuclear fusion can happen. Okay, then the atom will become neutral atom. There will be no ionized state, or there will be no separate for protons, neutrons, and electrons. And this happened at a particular point of time, and we name that point as epoch of recombination. Just think like this: there was a point of time in the history of universe when our universe changed from a ionized soup to a neutral atom point. We name that point as point of recombinations. As I pointed, this nomenclature is very confusing because there was no neutral atom before the recombination epoch. Still, people name it the epoch of recombination. I don't know why people name it, but we should go with the convention.
Okay, sir.
Thank you, Irene. We have another question from Vinayak Sanil. Vinayak, can you please unmute yourself?
Morning, sir.
Morning.
My question was on the basis of the inflationary theory that was put in the Big Bang cosmology model. So my question is, when we consider the inflationary theory, the expansion of the universe supposedly happens at superluminal speed.
Your voice is breaking. Excuse me.
Hello?
Your voice
Yes,
is
sir.
getting break. Yeah, now I can hear.
Okay, so the question is, when we consider the inflationary model, expansion supposedly happens at a superluminal speed.
Yes.
So, but special relativity does not allow superluminal speed.
Yeah. So
how can we reconcile these two contradicting facts?
Yes, special relativity says that nothing can move faster than speed of the light. Okay, it is not violating here also. Here, nothing is moving fast than the speed of the light, but the space is expanding. As I pointed earlier, when two galaxies or anything is moving apart, it is not actually galaxies are moving apart. The space is actually expanding, moving. So with this, there is no constraint of in the speed of the expanding space with special theory of relativity. The space can expand, and this inflationary model or inflationary epoch we introduce into this cosmology to explain many other problems like horizon problem. There are many problems. So it solved those problems without violating these special relativistic considerations. Space can expand. Space can expand with a higher speed.
Okay.
Thank you, Vinayak. We have another question from Ari Lakshmi. Ari Lakshmi, please.
Hello, sir.
Hi.
Sir, my question is, will the universe expand forever? Can Newtonian dynamics explain the expansion of universe?
Yeah, I pointed you at the end of the talk. What we are observing right now is the universe is not only expanding, that expansion is getting accelerated. Okay, so it will expand like this for a while, and we don't know our current understanding of dark matter is true or false. In 20-30 years, we may find a better, or we may find the best suitable candidate for this dark matter and dark energy. Then only we can precisely answer this question. But as of now, our universe will expand, not only expand, acceleration. There will be acceleration in the expand, and it will also become cold, 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 less denser, and this will go like that. Okay, to your second part of the question is, can Newtonian mechanics explain? Hello, hello. Can Newtonian mechanics explain?
It can be used to explain the universe.
Expansion of universe. Yes,
Yes.
yes. So we can derive the so in the cosmology, we normally use an equation called Friedman equation. I can show you that equation, but I am not going to explain it right now because of our constraint of time. Can you see my screen?
Yes.
So it was there in the end of the talk or the next section of the talk. Yeah, here it is. Here it is. Here it is. Okay. So for the expansion of universe is governed by this equation. It is called Friedman equation, and this A is called the scale factor of the universe. What that means, it's just like a ruler. Okay, this equation will say that what will be the length of, if you solve it, we will get the value of A. Okay, then what we can understand is what will be the length of our ruler at some point of time, at present, at 20 billion years back, at the beginning of time. Okay, so this equation will give the expansion of universe, and this equation first derived by Friedman by solving Einstein's general field equations. G mu nu is equal to some constant T mu nu, that equation, for a homogeneous and isotropic universe. But just by using Newton's law, one can derive this equation, and it's a very simple mathematics. You can find that derivation in a book called Introduction to Cosmology by Andrew Liddell. I think I forgot the chapter number. In that book, that person derived this equation. This is the Friedman equation governing the expansion of universe for a homogeneous and isotropic universe. You can derive this equation from Newton's laws of motion. Yes, you can. And if you want the derivation, just refer Introduction to Quantum Mechanics by Liddell. Are you satisfied with my answer?
Yes, sir. Thank you, sir.
Okay, thank you, Lakshmi. Next is Revati Krishna. Can you please unmute yourself?
Hello? Am I
Hi.
audible?
Yes,
Yes.
yes, audible, audible.
Yes, I have a question like after millions of years, whether it will be the same state as like that of the earlier itself, like whether the fourth dimension comes to an end.
So yeah. So the answer is that the state of the universe will change, and as I pointed you, our universe is expanding, not only expanding, the expansion is getting accelerated. So the state will definitely change, and the universe will become colder and colder and colder, and less denser and less denser and less denser. This is our current understanding. The change will change after millions of years. In few years, like in 10-20 years, we will get a more fundamental picture, because currently there are a lot of research going on identifying what are those dark energy and dark matter. Once we understand what are those things, then we can give a more precise prediction for the future of our universe. To Ari Lakshmi, this is the book. This is Introduction to Modern Cosmology by Andrew Liddell. This I can show you that derivation somewhere here. Yes, in the chapter 3 of Andrew Liddell, you can see the derivation of expansion of universe with Newtonian law.
Okay, we have a question from Kevin Abraham.
Yeah,
Kevin,
please.
Hello.
Hello.
Sir, can you hear me?
Yeah, I can hear you.
So when you were talking about like the dark universe, you told that stars can rarely collide, right?
Yes.
Yeah. So can that lead to a supernova?
No. What I meant by supernova, what our understanding with supernova is the end or the dying state of a star, bigger than sun or like that. Okay, yeah. That's the end of a star. That's what supernova is known as. So what was your question? It's saying that can the collisionless...
Yeah, the collision of two stars, like when two stars collide, there will be a release of massive energy, and can that lead to a supernova? That was my question.
No. So what I was telling is stars are not colliding. The galaxy clusters are colliding. Okay. What is a galaxy cluster? A galaxy cluster is a cluster of galaxies. Okay. One galaxy cluster contains 100 to 1000 galaxies. Okay. And when these galaxy clusters collide, it's like this. Most of the matter will go like this. Collision will go like the collisionless matter. Okay. But there will be a huge interaction between the gas and the plasma in this medium. Okay. If you consider these fingers as the stars, okay, and the gas and plasma will be there in between the stars and all. Okay. This will go like this, but this plasma and the gas will interact, and that interaction will produce huge, enormous energy. Okay, if you calculate that energy, it will go up to 10 to the power 64 ergs per second. That's a huge amount of energy. It's a massive energy. It will be the most energetic event after Big Bang. Okay, if you consider Big Bang as the most energetic event in the universe, then such incident, the interaction, the collision of galaxy clusters will be the most energetic events. That will produce a huge, enormous amount of energy, like 10 to the power 64 ergs per second. And as I pointed in the Boyer cluster slide, that temperature will give rise to X-rays through some process is there. Yeah, that was the reason for X-ray. And most of the stars will go like collisionless like this. There will hardly happen this head-on collision for stars. They will not collide. Most of the case.
Thank you.
Okay, thank you. Gogul Subramanian, can you please unmute?
Hello, sir.
Hi.
So my question is, since the space itself is expanding, does it affect the size of galaxies?
Yeah, it will definitely, because since the space is expanding, so there are two redshifts in our cosmology. One is called cosmological redshift, and other one is the shift in the spectral line. Okay, so what is meant by the cosmological redshift? Cosmological redshift means we have the picture of light, we have a picture of wave like this. Okay, if the space on which this wave is propagating is expanding, what will happen? The wave will also expand, because the space on which this wave is occupying or is vibrating is expanding. Then the wavelength of the light or the wave will stretch. That's what called cosmological redshift. Similarly, if the space is expand, definitely the size will expand of the galaxy will expand. But measuring that one is a tricky. Nobody ever designed an experiment to measure that expansion, as far as I know.
Okay. Dr. Shailaja Urpail.
Yes, sir.
Hi.
Okay, sir. First of all, let me thank you for a very informative and useful talk. So my doubt is that from your talk, I came to know that dark energy is responsible for the acceleration of the universe. And again, is there any chance for the universe to come into the singularity? That means where the Big Bang starts. At the same time, that what happens to the dark energy as the acceleration increases, whether the dark energy and the dark matter will increase and the baryonic matter will decrease, or is there any evidence or the study like that? So that is my doubt.
There was different epochs in the universe. Earlier, it was a radiation dominant. There was a radiation dominant epoch. There was a matter dominant epoch in the universe, and currently it is a dark energy dominant epoch. So, as of currently, the chances of going back to singularity is very less as of now, because the dark energy is the dominant one as of now. But again, as I pointed, we have to understand what is contributing this negative pressure or dark energy. What is responsible for this? Once we get idea of this thing, it may again change our picture. As of now, the universe will expand and get cooler. It will not go to a singularity as of now. As of our current understanding.
Okay, thank you, sir.
Okay, we have a question from Pravida. Pravida, please.
Hello, sir.
Hi.
Hello.
Hello.
Hello, sir. My question is, can we predict the fate of universe by dark energy?
Hello.
Hello. Can we predict the fate of universe by dark energy?
Yeah, that's what we are discussing for the whole time. As of now, with the understanding of dark energy, the fate is that singularity will not happen. It will expand. That's the current understanding of the fate of the universe.
Okay, next, Ganga R. Nair.
Hi, sir. Good morning, sir.
Hi, good morning.
Sir, I have a couple of doubts. So you said that density gets on, like it becomes less denser. So when we talk about density, is dark energy involved in it?
Yeah, density means the density, which I should have mentioned that thing. Density is I was mentioning about the matter density. This matter density includes dark matter and our baryonic matter. And one more point, as an astrophysicist or cosmologist, everything is baryon for us. There is no classification of like baryons or fermions, or there is no classification for us. Everything we represent or we call everything as baryons. So what I was meaning, matter density means dark matter and
So energy is not included in that.
dark energy. Yeah.
It is included or not included?
It is not included.
Yes, sir. Okay. So does dark energy also evolve more and more, or does its content remain the same?
Yes, that's the question we are looking for. So we don't know what is the source of this dark energy, or more dark energy is producing, or something is going. Is it conserved? These questions are not answered. So we don't know how this dark energy is producing, how it is increasing, or it is in a static state, or when the universe expand, the density of dark energy will change or not. Those are the questions which have yet to be answered.
So, sir, you said the acceleration is caused by dark energy.
Yes.
This question is same, but for the acceleration to continue, like acceleration is going on and on. So dark energy is that strong, or can dark energy forever cause that acceleration?
Can dark energy?
Like for the acceleration is going on and on. Like you
Yes,
said, it is forever.
it is from the observation. It is not dark energy presented there. It is the dominant one. It is the dominating one. It is the dominant one.
Okay, sir.
Okay, hope there are no more questions. Okay, if there are no more questions, let's thank the speaker. Cheryl.
Okay, sir. I'm grateful that Dr. Reju John was an alumnus of Mahatma College, Tiruvalla. Even though his topic was vast, he braved it and lectured about the fundamental observation of modern cosmology, coma clusters, dark matter, etc. It was a very informative section. Thank you so much, sir, for taking the time to lecture us on this topic. Let me invite HM Matthew ma'am to express the vote of thanks.
Hello.